go. So when you see the words maximum, minimum, highest point, lowest point, something like that, those are words that you're typically looking for the vertex of your quadratic, which will be the max or the min. So again, that's going to be the vertex. So words highest, lowest, maximum, minimum, you're looking for where the vertex is of your quadratic are. To find the vertex, or the highest, lowest point, you're going to use an equation from last unit. X equals the opposite of b over 2a. All right, so that has not disappeared yet. We're still going to be using that in this unit. More today, and then as we get back, learn more with our calculator tomorrow, a little less. But we will use that formula today. Other key phrases or words. You might see something where it says, when does a ball hit the ground, or hit the water, or how long is something in the air? When you see those phrases, we're going to be looking for the x-intercepts of the function. Okay, so we'll be factoring or using our quadratic to find those values. So today is pretty straightforward. We're going to start by giving you a graph, then we'll make a graph, and then we'll do multiple choice. But short day, just kind of ease you into quadratic. What? Is what? Straightforward for everybody. Because this picture right here I'm using in my Algebra 1 class later this week. Because they're doing quadratic.
Every time you talk about that, you always seem like upset.
I really do enjoy Algebra 1. It's just that I'm going to be quadratic modeling all day. Which is a little dry after a while. It's okay. No, I do enjoy Algebra 1. I like Algebra 1. Okay, so we have a graph. This is the height of a small rocket after 2 seconds. So you're given this model here. H of t is negative 16 t squared plus 128t. So this is the quadratic equation that's modeled by that equation. First of all, first question, how long is the rocket in the air? What would you say? 8. Yep, you launched right here at 0, goes up in the air, comes back down, it lands on the ground after 8 seconds. Now we're in a modeling unit, which means we need to use units. Okay, so 8 seconds. 8 means nothing in the context of real life. What is the greatest height that the rocket reaches? So greatest height, we're looking at the vertex here. What is the height that's the highest? 260. Yeah, 260 feet. So you shoot the rocket 260 feet in the air, that's almost a 3-story building. So you roughly, a story is about 10 feet. So almost 3 stories. Just a few feet taller than you? Yeah. At what time do you reach that maximum height? 4 seconds, okay. And that's 4 and the 260 together makes the ordered pair for the vertex, 4, 260. All right, that's what the next part is saying. So both parts of each ordered pair tells you a piece of information about the quadratic. Now, about how high is the rocket after 1 second? Here, look at your graph. I would say it's about 100, yeah, 100 feet. Now after 6 seconds, if I go over here to my graph, about how high are you here? I would say 190 feet. Good. Just about 190 feet. Now, intervals are coming back. We haven't had intervals since like the second unit. On what time interval is your rocket going up in the air? So when we look at this, we're looking at this part of the graph. Where is the rocket shooting up? So what time do you start going up in the air? 0, okay. And when you stop going up in the air? 4 seconds. Now there's 2 ways to write this. You can write an inequality. Say 0 is less than t is less than 4. That's one way to write this. Or you can use interval notation. If I used interval notation here, what symbols would go around the 0 and the 4? Not brackets. Parentheses. Now the reason we use either parentheses or the strict inequalities is because technically at 0, are you increasing when you're on the ground at time 0? No, you're just on the ground. You're increasing once you leave the ground, and then when you're at 4 right here, you're not actually increasing or decreasing, you're just at the top. So You're not increasing or decreasing, and then you start going down. So what time interval then are you falling back towards the ground? From 4 until 8. So then you have two ways to write this. 4 is less than t is less than 8, or from 4 to 8. All right. Lastly, we're going to use the equation they gave us to find the exact time, or the exact height, I'm sorry, of the rocket at 2 seconds. So how do I use the equation up there in blue to find the height after 2 seconds? Put it in for t, yep. It's close to 190, but we want to find the exact value. So I'll have negative 16 times 2 squared. Yes, you can use your calculator unless you really want to do all those numbers in your head. You can, but I would use my calculator since I'm letting you know. So we type that in, we'll find the exact value here after 2. It looks like it's around 190, but we want to know exactly. And around there, right? 2 looks like it's around 190. It's not going to be exactly though. You forgot a negative on your 16. So negative 16. What do you guys get? 192. Did you get this? I don't know now, Grace. Alright, 192. Not too bad so far. Alright, so the first one. Good job, Bobby. Alright, flip your paper over. This should just be okay to identify key phrases and know what parts of the graph you're kind of looking at. The next problem, we're going to make the graph. Right, so still not challenging, but we're going to focus a little bit on things that are algebraic, and we'll make the graph. Alright, so let's see. I have the equation y equals, okay, we're very chatty today. Bring it a little bit down, because when we're done with this, and I talk to you about schedule, you can all chat while you do your work, okay? So we have the equation negative x squared plus 6x. We're going to make this graph, and we're going to graph it on the domain, or on the x values from 0 to 6. So let's type this equation into our calculator. I think, oh, I still have a graph there. So type it onto your calculator, and you should see that you have that parabola when you hit graph. Now this is modeling the shape of tossing a ball. So I have a bucket of tennis balls and foam dice and stuff in there. So found tennis balls. I keep them not just for this purpose, partly for this purpose. And you think this makes sense, that shape, for when you toss a tennis ball. Because if I toss a tennis ball, it goes up in the air, it comes back down, it makes the parabolic shape. Okay? So it makes sense that when we shoot things up in the air, they come back down the other side. We're using parabolas to model. So go to your table, and we're going to plot those points. So we're only plotting on the domain from 0 to 6. You only have to plot those values. But take a second, go onto your notes, and make your parabola look just like what you had. It's going by 2's here, so make sure you're counting. And that's the parabola you should get once you graph this. This was actually, I was very surprised that the tennis ball was so much faster. I think I used it last year though. Algebra when he was doing linear regression. So we had to count down some tennis balls so that we were like measuring the height of the Alright, so we make our graph. Now, why do you think that I only had you graph from 0 to 6? Why didn't I have you graph the other part that would be below the axis?
You can't go negative. You can't go up.
Because this is real life problems. So this x-axis is kind of like the ground. You toss a tennis ball up, because then it hits the ground. You can't go. I mean, I guess you could burrow under the ground, but it doesn't make sense. So when I look at this graph, at what time x is the ball at its highest point? 3 seconds. All right, so I'm going to leave that here for a second. 3. That's the x-coordinate of the vertex. However, you need to know how to find that value algebraically, not just from a graph. And this goes back, I'll flip, you don't have to the front of our notes, where we said if I'm finding the words where I have to find the maximum min, you might have to use this x equals the opposite of b over 2a formula. So that's what we're going to use here to make sure we can do it algebraically, because you might not have a graph every time. You might not have a graph, you might have to find the time of the maximum by hand. So when I look at my equation, what's the opposite of b? B is what here? B is 6. So the opposite of 6 is negative 6 over 2 times what's a? Negative 1. Negative 6 divided by negative 2 is 3 seconds. And does that match what we got from our graph? Yes. Yes. Okay. So algebraically it matched what we had from our graph. Now, knowing that happened at 3 seconds, how do I algebraically find the maximum height? We know it's going to be 9 from our graph. But how by hand would I decide that it was 9 feet?
That's a good question.
Plug 3 into the equation, right? So 3 is my x to find the y value that goes with it. This is what you had this on your test last week. We would have negative 3 squared plus 6 times 3, which again you can do by hand or in your calculator. Negative 3 squared is negative 9 plus 18.
Negative 1. It's 9. It's positive
9 feet, not seconds. Positive 9 feet. Good. Which makes sense, we know, because the vertex of our parabola is at 3, 9. Alright, and lastly, algebraically determine when the ball hits the ground. So when we come back to our front of our notes here, we talked about the phrases hitting the ground. Well, I said when you do that, you're looking for the x-intercepts of the function. Do you guys remember how you find x-intercepts by hand? Put y in for 0 in for y, so I'll have 0 equals negative x squared plus 6x. And what do I do from there? It starts with an f. Factor. Yeah, it's factor this time. Solve by factor.
Factor that.
How would I factor this one? What do you always do first when you factor? GCF. What's the GCF going to be here? I would do negative x. You could do x, but I would do negative x because the first term is negative. So I'll pull out a negative x, and what do you have left inside the parentheses? X. Yeah. Alright, so I set the quadratic equal to 0. I factored. What do I do with each factor now? Set them equal to 0. Use the 0 product law. So I take each factor. It's all coming full circle now. Here's those reasons for it. If I solve this, what's the first x-intercept? 0. And I add 6. Where's the other x-intercept? 6. Now, which one makes more sense for the time when the ball hits the ground? The 6. Why does the 0 not make sense? Yeah, well, that's where it starts, right? Time is 0. That's where the ball started. Time 0. It doesn't make sense to hit the ground when you haven't started yet. So the 0 doesn't really make sense in this context. Right? So 6 seconds is. We good? Not too hard still. This is the easy day. One more problem. It's multiple choice. We're talking about a decathlete. Do you guys know what a decathlete is? They do everything. So what does deca mean? 10. So they don't have it in high school, but college and professional, there are decathletes. So they do things like javelin, the 200, the 100, the 400, the 800, long jump, high jump. They do everything. Javelin? This is what we're going to talk about now, the javelin throw. What's a javelin? That's like big spear. Stick with the pointy thing on the end. So you throw it. It's like throwing a spear. A decathlete.
I'm a decathlete.
Oh, what does dodeca mean? 12. No, that's Icasa.
Oh my God.
No, wait, no, Icasa's 20, dodeca's 12. You're right.
Oh.
Alright, so here's our decathlete. Oops, that's not a good picture. Well, not that I'm that great of an artist anyway, but here's my decathlete, right? And they're throwing a javelin. A javelin is the long little thing with the... Looks like javelin, right? And he's throwing a javelin. What shape does this javelin go? You can imagine that you're going to throw your javelin. It's going to come up like this. And what's going to eventually happen? It's going to come back down. So that's the shape that your javelin goes. You throw the javelin, it goes up. Now you can imagine that this path is, it's not the greatest picture ever. Obviously I should have been an art teacher. But it's a parabolic shape, right? Is that parabola opening up or down? Down. So what has to be true about our equation of a parabola?
Imagine if you drew it and went straight.
Can you imagine a parabola going down?
Yeah,
It's like a boomerang. Alright, what has to be in front of your equation for this parabola? A negative. So which ones can I eliminate? A and B. A and B have a positive 1 over 100, which would mean their parabolas look like that, which doesn't make sense to throw a javelin down and then it pops back up. Okay, so we're throwing our javelin, we're throwing it up in the air, it comes back down. C and D are almost exactly the same, except for the ends here. How do I differentiate between the two? How do I choose? What does that plus 3 and minus 3, what? That is the y-intercept.
And it can't.
So do you want a positive y-intercept or a negative y-intercept? Y positive. Yeah, you can't start. This negative means that your javelin was being thrown from underground, which just doesn't really make sense.
Andrew and I will start underground.
Okay, you'll be the exception. But in general, I think most of the athletes throw the javelin from above ground. So we're going to say that C is our final answer. Okay, not too bad today?
Yeah.
All right, so what I need from you